Yeah, so that is the problem, and the general problem setting here now from the summary, which is derived from the summary, is that we have to search for clusters in subspaces of the original feature space, and these subspaces, if we only talk about access parallel subspaces, we're talking about feature relevance. If we're talking about feature correlation, then these subspaces may be arbitrary oriented. Yeah? So there may be an arbitrary oriented subspace that is relevant in order to find a cluster of correlated objects. Yeah? So the challenge now is not only to find the correct cluster. There's a second point. Yeah, we want to find the correct cluster in each relevant subspace. Yeah, the search space here depends, of course, on the clustering algorithm. But the first thing is, or well, both are actually interchangeable. So we also, in addition to find the correct cluster, find the correct patterns, we also need to find the relevant or the correlated features, meaning the correct subspace of each cluster. And here, if we are talking about arbitrary oriented subspaces, the search space is virtually infinite, because all possible arbitrary oriented subspaces of a feature space is just, you know, anything. Yeah, it's just the whole spectrum. It's virtually infinite. Yeah? And even worse, those two challenges that we face here. So the second one is the general clustering challenge. But now, as we said at the beginning, we also need to take care about feature relevancy and feature correlation. And both challenges actually depend on each other, because in order to determine the correct subspace of a cluster, we need to know at least some cluster members, because otherwise we don't know the subspace, right? And in order to determine the correct cluster members, we need to know the subspaces of all the clusters, or at least of this cluster. Yeah? So we have a kind of vicious circle between these two challenges here. The challenges depend on each other. So we can only solve one if we know the solution to the other one, and vice versa. And that makes it quite hard to get a hands on that. So we have to break this kind of vicious circle somehow. And we see in some of the methods how we do that actually. Yeah, but to be honest, this kind of vicious circle, so the dependency of these two problems on each other is somehow technical. So it's a technical problem, obviously, but in practice, we just have, well, in general problem somehow to really look for, or to really define the correct patterns that we really want to find. Yeah. So here is once again this example of before, where we know somehow from the application we look for things that have a common correlation. That is probably what we want to know, or what kind of patterns we want to find, because the background knowledge, the doctors in that case, already tell us that please look for those patterns, because those patterns are probably exactly the kind of patterns we want to find, the disorders in that case. Yeah, so there is a kind of background knowledge already involved in this scenario, where we know what kind of patterns, or somehow have an idea what these patterns could look like, and what kind of patterns we should search for. And recall my comment on unsupervised methods, on clustering methods, that all those clustering methods are somehow search methods. We define what kind of patterns we want to look for, and then we search for that. Yeah? And that's the same here. If we know that our patterns look like linear correlations among subsets of features, we could try to look for that kind of pattern. And that's exactly what it is all about, so to say, here, also in these embedded methods. Yeah? But you see here in practice, it's not really easy, because, well, even if we know that this is exactly the correlation we have to look at, yeah, this one here, so this is the relevant subspace here perpendicular to this correlation. If we already know this is exactly what we need to look for, or look at in order to find the green cluster you see if we project all the points down here, we have a real hard time to identify the green cluster. Yeah, so it's not that easy in practice. Just if we know that we look for linear correlations and then we project everything on these perpendicular subspaces, everything is fine. No, not necessarily. Yeah, so even if we found the relevant subspace, we still may have a hard time to find the correct cluster as it is down here. And the same holds true actually for the subspace of the red cluster, and maybe also for the subspace of the yellow cluster. Yeah? So it's not a really distinctive pattern in the corresponding projection. Yeah? So here the clusters and noise are not really separable in the correct subspace, so to say. Yeah? And this makes it really hard in practice. Yeah, that somehow looks or says or tells us that we probably need to look for a new cluster model. Yeah, so and the cluster model is actually what defines the type of pattern we look for. Yeah? So we probably need to really take care of how to define the pattern that we look for when we apply the method. Yeah? So and that brings us to the question: what is the concept of similarity of all the cluster members of all the members of a cluster? Yeah. So the idea of a cluster is that all the members are similar to each other. So they share some kind of similarity, all the members of a cluster. And what is this concept of similarity or for this green cluster or for the red cluster or for the yellow cluster? Yeah. So and that is exactly the point. If we know what kind of patterns we want to find, then we need to at least try to define the patterns accordingly. Yeah? And that is sometimes what it's all about. And then you see that clustering algorithms are nothing else than search methods that look for that particular pattern. Yeah? And most of the embedded methods, clustering methods for high-dimensional data we get to know in the following now are specific methods that look for specific patterns that happen or that may frequently happen in high-dimensional data. They need not to happen in your particular data set, but at least they happen frequently or in many high-dimensional data sets. Yeah? So keep that in mind always when we now get to know about different clustering methods. And since it is really a plethora, there's really a plethora of methods out there which deal with clustering high-dimensional data, because they are kind of embedded methods, integrate feature selection, feature relevance analysis into the clustering method. We try to give you a kind of taxonomy to somehow navigate through all those different approaches, because they have some kind of there's a taxonomy of approaches, and these three classes of approaches, all these approaches in the corresponding classes somehow follow some specific properties of the patterns that they look for. Yeah? So we have subspace clustering algorithms, which are first of all restricted to access parallel subspaces. So they don't care about correlations among features. They just look for relevant and irrelevant attributes, and they just want to identify the relevant attributes for a cluster. But they don't consider non-access parallel arbitrary oriented subspaces, meaning they don't consider correlations. Yeah? And they try to find all clusters in all subspaces, and in this sense they allow overlapping clusters, like the baby shape game, where points may be clustered differently, so end up in clusters with different points, with different other points in different subspaces. And they are typically also associated with a specific algorithmic search strategy, at least if it comes down to what is the correct subspace of a cluster, because they typically use a bottom-up subspace search and integrate that into the clustering algorithm. Secondly, we have projected clustering algorithms that are also restricted to access parallel subspaces as those here. But the most important point is that here now in the projected clustering algorithms, each point is assigned to exactly one or no subspace cluster. Yeah? So one cluster or noise. So there is no overlapping clusters allowed. Yeah? So projected clustering is a kind of each point goes to at maximum one subspace cluster. Here in subspace clustering algorithms, points may go to different clusters in different subspaces. Yeah? So projected clustering is somehow a little bit comparable to normal clustering algorithms that typically try to find this disjunct partitionings. Yeah? Typically, the subspace search is top-down, yeah, which is interesting because this one here is typically bottom-up. This is typically top-down here in projected clustering algorithms. And then as a third one, well, the fourth one, which is in between here, are so-called pattern-based algorithms. They have a completely different idea, and we will talk about that when we care about pattern-based algorithms. And the third one, or the fourth one, so to say, is correlation clustering, which are approaches that are now also considering correlations. So they explore arbitrary-oriented subspace clusters or subspaces. Clusters may be now in arbitrary-oriented subspaces, and typically they are somehow generalizations of projected clustering algorithms, but need not to be. So typically each point is assigned to one subspace cluster or noise, but some also allow overlapping clusters, but anyway. And there are different approaches, bottom-up and also top-down subspace searches, because this is the most general form of problem, yeah, arbitrary-oriented subspace clusters. So those two here are kind of special cases of correlation clustering because they are restricted to access parallel subspaces, and correlation clustering algorithms are not. Just one more thing here before we start. You see we start here right away, but one more thing. Correlation clustering, the term correlation clustering is also existing in another context in machine learning, which is has nothing to do with high dimensional data and subspace clustering and stuff like that. So just that you know, in our context, we use correlation clustering for those approaches that explore clusters in arbitrary oriented subspaces. So